Okay. Yeah. Hello, everyone. Friends, colleagues, good morning, and welcome to the 2024 CEDAR workshop, and most importantly, welcome to Student Day. My name is Andrew Pepper, and I am the outgoing CEDAR Science Steering Committee student representative, and I am delighted to see you all here today in sunny San Diego for this week-long conference. If this is your first one, hang in there. It will get easier, and you'll be in the swing of things soon enough. If you're a seasoned veteran like myself at this point, you already know what to expect. You'll hear, I am delighted to share the stage today with the incoming student representative, Sophie Phillips, and you'll hear more from her in a bit. But I wanted to thank you all for your thoughtful feedback and input this past year. Sophie and I really value your feedback, and we use it every step of the way in the planning process. We strive to make this day as informative, interactive, and welcoming as possible, whether it's your first CEDAR or not. Sophie has an absolutely fantastic agenda in store for you today, and I think I've labored on just a little long enough, so please help me in welcoming the incoming student representative, Sophie Phillips.
Well, thank you, Andrew. Hello and welcome again to the 2024 CEDAR Student Day, a day by students, for students. As Andrew said, I've been working with Andrew and a wonderful volunteer student committee for the past about year or so to develop the agenda, contact the speakers, and we've really created a great presentation for you today. I think we met last August was our first meeting, so it's surreal and exciting to see it all come to fruition. So our vision for today's agenda is our theme of the atmosphere that we live in. And if you'll, I have my slide stick here. And with this theme, we had two goals in mind. The first is, of course, to understand the atmosphere that we live in, the dynamics, everything that goes into it. And so we've conveyed that with our first morning session of lightning talks, of course, the science that we're all here to do, and that makes us great researchers. The second half of the day, I hope we'll focus on the other part of science that is as equally important, but perhaps not as addressed. And that's the atmosphere of being a grad student and being a researcher. And there's parts of science such as science communication. What kind of career do you want to go into with the career panel? Proposal and grant writing. And what do you see if you see a situation in your work environment that you may not be comfortable with through our bystander training? And so with those goals in mind, I've developed this agenda with the wonderful team that I previously mentioned. And so here it is, the agenda that I'll take you through now. So in the morning, we'll start off with the lightning talks. We got 5 really distinguished scientists that are going to give you some of the basics of topics that you're going to hear throughout the week through various presentations and tutorials. Then we'll have a Q&A where you'll get to ask them questions. And then after a break, we'll hear from NSF, and they'll tell you about proposals, grant writing, and what they do for CEDAR specifically. Then we'll hear from Caitlin Greer about grand challenges at CEDAR. What are they? Where's the science involved in them? And how can students get involved? Then we'll take a lunch break. And after that, we have a really exciting science communication and networking talk by Rachel Lenz, who is a professional science communicator with a GDC mission. And then we have a sort of choose your own path section in the afternoon. If you're more interested in models and hearing more science talks, you can go to Honongwoo's CCM and MAGE model tutorial. That'll be in the East Coast room. Or if you're more interested in hearing about what career paths there are for you in research, you can stay in this room and hear about from our career panel, also made up of very distinguished scientists in the field. Then we'll take a final break and we'll come back into this room for a DEI talk on bystander training. What can we do as students when we see a situation that we're not comfortable with? And for that, I've invited a scientist in the San Diego area. Her name is Brooke Engel, and she works with Hewitt and Packard Company. And she'll come in and she'll talk to us about that. And after that, we'll do an outdoor activity. Perfect. Yes?
Agenda's in a different order than the website.
Yes, it's in a... We're going to follow this agenda that I think I sent out to you in a PDF. Yeah, apologies, the website agenda didn't get updated with this one. But perfect. So today, as I said, you'll be able to ask lots of questions for our wonderful presenters, and to do so, we'll be using Slido. If this is your first time at CEDAR, you'll just go ahead and click that or scan that QR code, and you'll be able to ask questions there, either anonymously or you can add your name to them. And when you do, especially for our lightning talks, if you could just name the person that you are addressing the question to, that would be a huge help. So I'll leave that on the screen so people can take photos, getting ready to ask lots of wonderful questions, I'm sure. Perfect. And I think the QR code will also be available later in the day if you change your mind about asking questions. Okay, I'll give 10 more seconds. Perfect. Everyone's got their photos. Wonderful. And I just want to also mention and promote the student activities do not end with Student Day, although Student Day is tailored to students specifically. The student presence at CEDAR does go on throughout the week. And so after Student Day tonight, feel free to unwind with a movie in this room. Tomorrow at lunch, there'll be a mentor-mentee lunch where we will pair you with scientists in the field. You can ask them questions and get their guidance on any sort of questions you want to ask them. Monday night, I should change that. It is now just a hangout night in Porthole Room. I'll bring board games. We'll just unwind with some board games instead of trivia. Tuesday night, we'll all meet up and go out for karaoke. Tuesday and Wednesday are the poster sessions. I'm sure many of you are presenting. Please go and support your fellow students and hear about all the great science that we're doing. And then finally, on Thursday, there will be a student lunch in which we can give our feedback to CPAS about what we'd like the future of CEDAR science to be from a student perspective. And as you can see, there's another QR code. This one's for the CEDAR student WhatsApp. So if you're not in it already, feel free to scan that, and we can chit-chat there. So I'll leave that on for 5 seconds so people can scan that QR code. Perfect. See a lot of phones out. Wonderful. It's a fun group. All right. Perfect. And if you want to see it again, feel free to come to me after. And that is it. So now I am happy to welcome the chair of the CSSC, Dr. Mark Condi, to give a few opening remarks. Thank you.
Well, thank you, Sophie, and welcome everybody here to San Diego for this CEDAR meeting. I was going to say which number it was, but I've forgotten, and there's some debate as to when we first started. As Sophie said, my name is Mark Condi. I'm from the University of Alaska in Fairbanks, and I have the honour and responsibility of being the chair of the CEDAR Science Steering Committee. What that means in practice is I've spent the last year worrying about this meeting and trying to get everything organised and worrying if everything was going to go smoothly. And I would like to start by just thanking Andrew and Sophie and all the people they've been working with in the last year just to get this session organised. It looks fantastic to me, and I'm really looking forward to it. As both Andrew and Sophie said, you know, some of you this will be the first time you've come to CEDAR, others have been here a few times, but CEDAR can be quite intimidating, especially first time. I did my graduate work in Australia, and I came here in 1993. In the first week in June, and then the second week of June, my postdoc advisor said, you should go to CEDAR. And, you know, coming from Australia, which was a fairly small space physics community, to the US, I was just completely overwhelmed by the experience of being at CEDAR and all the range of disciplines and things I didn't understand that were presented, and I felt really quite intimidated. I'm not sure that feeling ever goes away, but I can tell you that just by diffusion, year after year, you see more things and it all starts to make sense. So if you feel a bit overwhelmed by just the range of topics and what's going on, hang in here. I think, as Andrew and Sophie said, you know, it does sort of get better. It becomes more natural for you. I wanted to say what I think CEDAR is. There's the science we do, but the actual organisation of CEDAR is all about a community of scientists and people coming here. You know, why do you bother coming to San Diego? Why do you make this trip here? You come here for the people in the room and for the people that you interact with in the hallways and the poster sessions. So please do try and use this week to talk to your fellow students, try and talk to the PIs, see what other people are doing, see what's going on. CEDAR is really important. And I think students are really important. We have this tradition at the start of our first morning on the Monday for all the students to stand up. And when you look around the room and you see the people standing up, the people who are standing up at the student introduction, they're the ones who are going to be the program managers in what will just feel like a blink of an eye to you. In 5 or 10 years, you'll be leading big projects, maybe program managers going into the field, proposing new ideas. So, it's the students who are going to be the ones that carry this field forward. The other thing that I really want to emphasise is the importance of DEI. As I said, this is a community, and we need to be inclusive. So, I guess this would be more for the senior scientists, but everybody needs to. If you see someone who seems a bit left out, go over, talk to them, introduce them yourself. Try and build that community and be inclusive. So we've got lots of DEI activities this week, and they are really important. So lastly, I just want to thank everyone here for coming. A meeting isn't just us organising stuff. A meeting is what people present and what people bring to the meeting with the posters and the presentations and the talks, and you're all contributing to that. So thank you for that. I think with that, I will hand back to the organisers here. Enjoy your student day. I'm looking forward to it. I'll be watching, and I'm really excited. So thank you.
Great, thank you, Mark. And so with that, I'm excited to kick off our day with the morning lightning talks, and starting with Dr. Komal Kumari. Dr. Kumari, an ASP postdoc fellow at High Altitude Observatory affiliated with the National Center for Atmospheric Research, specializes in studying nonlinear wave dynamics within the upper atmosphere, covering regions from the equator to the poles. She earned her PhD in physics from Clemson University in May 2021, and subsequently served as a postdoc researcher at Arizona State University's School of Earth and Space Exploration until December 2023. With 7 years of expertise in handling observational and model-assimilated data, Dr. Kumari is skilled in the analysis of satellite temperature observations, ground-based scanning Doppler imager data, and meteor radar observations pertaining to winds associated with tidal wave scale, planetary wave scale, and traveling gravity wave scale phenomena. She's primarily interested in researching the role of wave coupling processes in connecting the dynamics of the lower and upper atmosphere. Please welcome the former student rep from when I entered CEDAR, Dr. Komal Kumari.
Well, thank you, Sophie, for the introduction. Good morning, everyone. Let me see the pointer. Okay, how do I go back? Okay, yeah. So, okay, I think it's wonderful. We are starting our day with this talk, Mesosphere-Ionosphere-Thermosphere coupling. It is basically, it embodies the core of what we study in our community. Basically, this coupling is what predominantly governs the dynamical aspects of space weather at all locations. And that is why, as a scientific community, we want to understand the role of coupling in space weather physics in near Earth space region. And we want to feed, based on our understanding, we want to feed that in the computer model to do the accurate prediction of space weather. Now, for space weather prediction, it is important that we can predict the ionized state of atmosphere accurately, because any kind of perturbation in ionosphere or ionized part of atmosphere has severe impact on navigation and communication. Then it is also important to predict atmospheric compositions because we have spaceborne instruments in the near Earth space region, and they can experience a drag due to atmosphere, and it can basically change their orbit. So in order to track these instruments accurately, we need to predict accurately the atmospheric composition. So we have several study tools that we use to study the near Earth space region, and the coupling mechanism between mesosphere, thermosphere, ionosphere. So it varies from ground-based instruments such as radars, lidars, all-sky imagers, GPS receivers, to space-based instruments such as satellite, which is, for example, cosmic, icon, gold, timed. Then we also have sounding rockets. And then we also have some numerical models driven by observation, and also like free-running models driven by physics. Now let's get to the physics of what really governs this coupling between mesosphere, thermosphere, and ionosphere. So the driving factor is the ion-neutral collisions, and which is why the ionized part of atmosphere and neutral part of atmosphere is coupled. So the neutral part of atmosphere is basically what I see. The mesosphere and thermosphere here is what is representing the neutral part of atmosphere in this coupling process. And when the neutral molecules in the neutral atmosphere gets ionized by solar radiation, it creates ionized part of atmosphere. So the ionized part of atmosphere and the mesosphere-thermosphere region, they are co-located, and due to which we have ion-neutral collisions going. Now, this collision depends on neutral and ion density. So, let's see, yeah. Okay. Oh, wow. Oh. So this is the plot where you see how the density of ions and neutrals changes with altitude. So on the left, on the right, you have the neutral molecules and the neutral atoms, and on the right, on the right you have neutral, and on the left you have the altitude profile of ions. So what you see that with altitude, the density is depleting, so your collision will also, so basically there is more density, more collision. So as you go up in altitude, the collision is less and less. And this ion-neutral collision is happening at all locations all the time, and it is happening both at global and local scales. And that's why it is complex to study them. Now, how these coupling is playing role in the space weather dynamics is basically both through chemical and dynamical processes. Now, what I mean by chemical process, so as the ions are being formed by photoionization of from the sun of the neutral molecules. So you see that in thermosphere you mostly have, oops, never mind, sorry. Yeah, so in thermosphere you have mostly nitrogen molecule, then atomic oxygen, and then also molecular oxygen. And the photoionization kind of creates O+, N2+, and O2+. And then, due to ion-neutral collision, these ions can further interact with neutrals, and that chemical process is what can change the thermospheric and ionospheric density. So, for example, you see this reaction here. I'm showing that, for example. So. What is happening that O+ ion is interacting with N2 molecule, neutral N2 molecule, and forming another set of ions, which is NO+. And this reaction is kind of governing the loss of O+ ions here in the thermosphere, while in the other set of reaction, you see that the O2+ ion is interacting with the neutral atomic oxygen, and which is producing O+ ions here. So this reaction is an example where you can see how the O+ ion density O+ can be produced or lost as a result of chemical reactions. And this is happening because ions and neutrals are colliding. Now what about the dynamical process? So as neutrals and ions are colliding, neutral can transfer some of the momentum to ions and drag ions with itself, and that can create electric field and currents, and we already have Earth's magnetic field in the picture, so that pretty much generates this some plasma electrodynamics processes which can couple which can redistribute the plasma with respect to different altitude and latitudes, and this is what can also couple the lower part of ionosphere, which is E region, and upper part of ionosphere, F region. So this was very little summary of how this coupling is kind of may impact the space weather dynamics. Now a little bit more about how due to dynamical process, the neutral can influence ionosphere, and there are several phenomena we study as a result of this. And ionosphere can also put feedback to neutrals. So I have listed some of the phenomena that we study as a result of neutral influencing the ionosphere. And this is such as neutral wind dynamo, equatorial ionization anomaly, sporadic E layers, equatorial plasma bubbles. So basically what is happening that as the neutral wind basically can move ions either along the magnetic field lines, which is the animation you see on the top. Never mind, I always press wrong button. Okay, yeah. Yeah, so the animation that you see on top is basically showing you how the neutral is moving ions along the field lines. Then neutral can also move the ions perpendicular to field lines, and that is what basically generates the equatorial fountain effect, where the plasma is moved away from the equator and deposited back at 20 degrees north and south magnetic latitudes. So that I'm basically talking about this phenomena. So all I want to say that the neutrals can move ions either along field lines or perpendicular to field lines. And one of the, due to this equatorial fountain effect that I just explained, what happens that if you look into the ion density near the equatorial region, you will see the two bands of enhanced ion density. So I think this will be more covered in detail in the upcoming tutorial talks. So I'll just move on here. And then we also have ionospheric feedback to neutral, when the ions can put a drag to neutrals and changing the speed and direction of neutrals. So, all right, so going forward, now there's other aspect of dynamical process, that there is the mesosphere and thermosphere region is closely coupled to lower atmosphere. Lower atmosphere, what do I mean? Is troposphere and stratosphere. So basically what's happening that in the lower atmosphere you have several driving mechanisms which generates a spectrum of waves. And when these waves propagate upwards, their amplitude increases exponentially. And as they reach mesosphere, lower thermosphere region, around 100 kilometers, they can break and transfer a lot of momentum and energy release. And they can also subsequently generate secondary waves due to breaking of primary waves. So this, due to this process, basically the coupling is happening between lower and upper atmosphere. And since we have spectrum of waves, from gravity waves, atmospheric tides, planetary waves, all of them have different periodicity and different wavelengths, going from minutes to hours to days. And the wavelength going from tens of kilometers to 10,000s of kilometers. So basically the lower atmosphere and upper atmosphere coupling is happening on multi-scale. And as the neutral atmosphere interacts with ionized part of atmosphere, this multi-scale kind of dynamics is also imprinted in the ionized part of atmosphere. So, okay. Now, what is important that we want to understand how does this coupling impact the the ionized part of atmosphere and neutral part of atmosphere, especially during space weather events. Now, you can have space weather events either originated from above or below. So above means you can have geomagnetic storm, aurora, solar flare, solar eclipse, and then also you can have space weather events generated in the lower atmosphere, such as volcanoes, sudden stratospheric warmings. All right, so what happens during geomagnetic storm? What is happening that you have at polar latitudes during storm, the ion-neutral collisions increases because of more ionization. So the ion and neutral collision increases, which kind of generates generates heating of the atmosphere due to Joule heating, and which is basically the frictional heating. And due to this heating, the atmosphere expands, and the neutral nitrogen molecules is moved up in the atmosphere, and due to which, as I showed the chemical reactions in the third slide or so, that this nitrogen molecule can due to nitrogen molecule, you can have loss of O+ ions. And then you also have the surge of the wind from polar to equator ward region. And because of all this, you basically have then the downwelling of neutral molecules at equatorial latitudes, and there you have more production of O+ ions. So because of this, basically during storm, it was observed from GOLD satellite data of in the thermospheric composition density ratio that it can bring up to 60 to 70% change in the space weather dynamics during storm. Do I have time? 2 more minutes? All right. So I have, okay, so before I go to the next slide, if you want to learn more about the space weather physics during storm, go to this session. We had a huge storm this year around Mother's Day. So yeah, please go to this session on Friday to learn more about it. Now, what happens when there's a space weather event coming from, originated from below, especially the sudden stratospheric warming? So what is happening in the sudden stratospheric warming? There is a disturbance of polar jet, and because of that, the stratospheric temperature suddenly increases and the wind reverses, and because of that, your wave coming from below, their amplitude changes. And first of all, due to the coupling of E and F region in the ionosphere and the dynamo process, you basically see that the amplitude of wave that was increased due to SSW, it is also imprinted in the ionospheric ion density. So which is what this plot shows. This is basically obtained from cosmic data of electron density. Then also in terms of composition, what is happening that during SSW you have the upwelling of neutral molecules at the equatorial latitude and downwelling at the polar latitude. So because of that, your the composition O by N2 ratio is also changing. So that was observed from GOLD data that there was depletion at the equatorial latitude during SSW region. Okay, so again, you have a SSW session as well on Thursday, so please go to that session if you want to learn more about it. Then last example that I want to show that there was this huge volcanic explosion, Hungatonga explosion, on 15 January 2022, and last CEDAR, there were several talks over it. Basically, due to this volcanic eruption, the LAMB waves and gravity waves can generate, and it was seen that there was conjugate concentric ionospheric perturbation as a result of that. So I won't go in details of it. So please go ahead and look. There are several papers over it. So that's it for ion-neutral coupling. So basically, the ion-neutral interactions are impacting the space weather dynamics through both chemical and dynamic processes. And multi-scale coupling mechanism is happening, mainly due to coupling from lower atmosphere. Well, I didn't explain the quiet and active geometric periods, but what I mean by active is when you have storm, and what I mean by quiet period, when you don't have storm, you have basically the space weather events coming from below. So during those events, it's really important that we understand and predict the coupling effects on space weather. And the key takeaways for student participants: identify open questions and gaps through attending all the workshop sessions, examine how the observations and models are being used to study the space weather events. Thank you.
Yes, thank you, Dr. Kamari, for that lovely presentation. Our second speaker today will be talking about the topic of gravity waves, and that is Dr. Jonathan Snively. Dr. Snively is the director of the Center for Space and Atmospheric Research and professor of engineering physics at Embry-Riddle Aeronautical University. He graduated from Pennsylvania State University with a PhD in electrical engineering and was recently appointed the new Sabre instrument PI, which is on board the NASA timed mission. Oh, no?
That's Jay. That's what it is.
Oh, excuse me. Sorry.
It's actually my fault because I forgot to provide you a bio. That was the one thing I didn't do.
Yeah, sorry, folks. He does work for Embry-Riddle, though, I promise. It's okay. Please welcome to the stage Dr. Jonathan Snively.
Thank you very much. No, it's totally my fault. Okay, so I want to make sure that I know how to operate this thing here. The play is the next slide. This is the previous slide. And what does this button do? If you point it at that one. Oh, there's a monitor. Oh my goodness. Okay. This is life-changing that I actually realize that there's a monitor here. So I don't need to look at this when I'm pointing. Okay. Thank you very much. My name is Jonathan Snively, and I apologize that I did not provide my bio information, and this is totally my fault there. So I would like to talk to you about the spectrum of gravity waves, and this is really a broad spectrum, and I'm only going to cover parts of it that are in particular the small scales, the waves that have periods that are below hours and have scales that are, for example, tens of kilometers to hundreds of kilometers, below thousands. The nature of the dynamics of the upper atmosphere are highly multi-scale. So even when we're talking about gravity waves, we're also very interested in the context of other waves which are propagating and waves that they're interacting with. And as well, we're really interested too in their effects, which keep cascading down to smaller and smaller scales to turbulence. As well, we're interested in coupling across systems because gravity waves will interact with the ionosphere. Matt Zettergren and others will talk about that separately. And in addition, we're interested in how atmospheric sources in the lower atmosphere will be effectively generating gravity waves at high altitudes that perturb the ITM system, the mesosphere and lower thermosphere, and the ionosphere. So this talk is intended as a visual introduction to gravity wave propagation and effects. And the purpose of this is to help you build a bit of visual intuition behind the dynamics of the waves. When we talk about specific processes, very often we're looking at what those processes are doing. We're looking at the effects, we're looking at how it connects to a system, or we're looking at how you parameterize them to describe a model at a large scale. Or you're looking at some wiggles in data. Looking at the overall wave field, though, it's really complicated, but you have to break it down into little bits or else you can really easily get lost or not have the visual intuition necessary to make connections. So I think we're all familiar back to 8th grade physics or so, the concept of longitudinal and transverse oscillations in a medium. When you have a wave, you might define how the medium is actually moving relative to the propagation of that wave. So when you think about transverse oscillations, you picture the up-down motion of a fluid relative to a wave that's progressing in the perpendicular direction. So similarly, you have longitudinal or compressional waves, perhaps, where you have a progression of a wave along the direction in which the medium is moving, like a classic acoustic wave. But the waves in the atmosphere are a lot more complicated because you have two things going on. One, we're interested in an atmosphere that is under the influence of gravity. So this additional force is going to add a really important geometric consideration for wave propagation. But we're also interested in waves that span a wide range of frequencies, so that depending on how you disturb the atmosphere, if you're effectively lifting it and displacing it, or if you're effectively compressing it, it's going to respond differently with different kinds of waves as it corrects for that. So when you think about water waves, you might immediately assume that this is kind of a transverse wave motion. You have up-down motions as the waves progress outward after you drop the pebble in the water. That is not quite the whole story, because you also have this circulation that's occurring just below the surface. There's a little bit more to a water wave, depending on the depth of that motion relative to the fluid medium. Now, waves in the atmosphere have a different situation because you don't have this hard boundary. You have a continuous, squishy boundary that's the whole atmosphere. And depending on the nature of fluctuation, sometimes those waves will get trapped in one region of the atmosphere due to the way in which temperatures, densities, or winds vary with altitude. But at other times, you have a nearly free propagation of a wave. It's effectively swimming up as high as it can to the space environment even. So internal gravity waves, and especially waves that look like this here, this one here is really clearly trapped near the troposphere, but waves that are generated by storms can be extending to very high altitudes. Now, when you have a big source, look at this example from Hungatonga. I'm really pleased that Kamal mentioned this one, because this is a dramatic case where you're imposing an enormous impulse to the atmosphere, and you're going to have a very wide spectrum of waves, including both acoustic and gravity waves propagating through the deep atmosphere, and as well, you're exciting trapped modes, and you're going to watch the atmosphere ring for days. Some of these waves will be producing secondary waves. You'll see signatures at all relevant timescales, and that's a really serious, dramatic example. But we're interested also in understanding the limits. So the gravity wave dispersion relation is one thing, but what I like to talk about is the acoustic gravity wave dispersion relation, and this has two branches. The reason to worry about two branches is because you have some waves that are more on the acoustic side of things, or are literally just acoustic waves that are excited when you have a source that is effectively squishing the atmosphere versus displacing it. So if you're able to lift and displace the atmosphere, it's going to reestablish its equilibrium and radiate gravity waves. But if you're simply compressing it, it's going to, depending on the time scale over which you compress it, it's going to radiate acoustic waves. So when you have stratified atmosphere, you have a characteristic density scale height. Your density is decreasing by 1/e over some distance of maybe 6 to 10 kilometers. And when you have wave scales that become very, very large relative to some factor of the scale height, that means that you're going to have a very hard time exciting a propagating wave along that direction. So it doesn't mean you can't squish the atmosphere over those scales. It just means that it won't propagate as a wave. And if you are moving slow enough to be able to lift the atmosphere instead of purely squishing it, you're going to also generate gravity waves. So looking at both sides, both branches of the acoustic gravity wave spectrum, is probably important, especially when you get to the ionosphere, because you're going to see signals of both. So if a particle is vertically displaced, it is going to tend to oscillate at a characteristic frequency, and that frequency is the Brent-Weissler frequency. In parts of the atmosphere, this is going to be closer to a 10-minute period, maybe a 5-minute period at shortest, and these oscillations are effectively vertical motions of the atmosphere following a disturbance to that stratification that lifted or displaced or heated some parcel of air so that it moved upward or downward. Now, as this fluctuation evolves, you effectively are going to be readjusting the original disturbance location by radiating waves away from it. So kind of swimming away from this disturbance, or progressing away, sort of like having the ripples around your pebble. You're going to have gravity waves propagating upward and outward. And you can visualize these a little bit, again, like kind of doggy paddling through the atmosphere. You're going to have a phase progression. The phase progression of the gravity wave lines of constant phase is downward and outward. The group velocity is perpendicular to that and upward and outward. And this is something that I think makes them a little bit non-intuitive, especially when they're freely propagating like this. So a cool thing, though, it seems non-intuitive, but this actually hints at the dispersion relation of gravity waves, because the angle at which a wave is propagating is actually a function of its frequency. So if you have a high-frequency wave, it's going to tend to take a more vertical trajectory. If you have a low-frequency wave, it's going to take a more horizontal trajectory, propagate more more outward. And interestingly, that frequency is also going to vary with the winds because it's the intrinsic frequency that determines that angle, and I'll talk about that separately. Now, because this is a real multi-scale problem, the atmosphere has a wide range of wave scales that it can support, all the way up to, of course, ones that care about the fact that the Earth is spherical and that it's rotating. For example, solar tides and planetary waves, and as well inertiogravity waves that are approaching scales for which rotational forces affects matter. We're not going to consider those in these. We're looking at waves that can fit in a nice box, and in particular, those that have spatial scales well under 1,000 kilometers, temporal scales under hours. So when we look at these waves, we're usually observing them through specific layered features of the atmosphere. For example, you might be measuring an ergo layer. You might be measuring a specific density that you can quantify through some remote sensing technique, for example, the state of the ionosphere, or you can excite some sodium and measure its response to profile the basic mesopause region. And when you're looking just those fixed layers that are measurable, you're missing the whole picture of waves that are below and above. So one of the things that is exciting with models is that you can kind of capture what's going on and understand the evolutions outside of where you're directly able to observe. So I find models kind of rewarding. This is actually a very, very simple model simulation in the background here of just what happens when you have a very basic plume disturbance at the left side, which is r equals 0. The bottom corner is z equals 0. This graphic extends up to around 350 or so kilometer altitude. Those waves are progressing outward, and it includes both acoustic and gravity waves. So when we look at these kinds of figures, we'll know that there is this spectrum of waves, including both acoustic waves and gravity waves, and is extending through the thermosphere. That's also the ionosphere. And if you're interested in the ionosphere, there are many, many ways to measure its dynamics. Now, what's especially cool about this is that you see all the time waves just like this above sources. So when you have a big convective storm, it's going to be producing dynamics and vertical motions and heatings that are at time scales that are able to generate acoustic gravity waves. You're going to see oscillations in the ionosphere that are of short enough period to be effectively acoustic and of long enough period to be effectively gravity waves, and those are going to be progressing outward from the disturbance. And these figures here are from ionospheric data. On the right side here, this is total electron content provided by Pavel Inchin, and I just selected a date at random. This here is, these are the acoustic gravity waves with shorter periods than 10 minutes that are progressing to the south here. And on this side, you have gravity waves that are evolving to the north. And this is, again, just a total electron content map selected at random. But there's a long precedent for these kinds of data. This is a figure from Azim et al. And a corresponding air glow image provided from a paper by Miller et al. And this is, again, above a thunderstorm in Texas. This is probably a thunderstorm in Oklahoma or somewhere else over here. But again, you have an effect that extends the whole way through the atmosphere associated with wave dynamics. This contributes variability. And not all of that variability is captured in the specific layers that you can measure at a time. Because the atmosphere is stratified and you have this decrease in density with altitude, your fluctuations grow stronger and more vigorous as you reach high altitudes because of conservation of energy. But energy can only be conserved to the extent that it can, remain linear or not be dissipated through some other process. So the two competing effects that we'll see for waves that reach high altitudes are viscosity due to the rarefied atmosphere, because your collisions are fewer and further between, or the nonlinear growth of fluctuations, which is eventually going to, if sufficient, result in the wave simply breaking down. This is all complicated by winds, though. Winds have a huge effect. As noted, winds provide Doppler shifts for a wave, and this wave here is kind of a spectrum with 40 to 80 kilometer initial wave scales, and is passing through a Cartesian slice of winds. So this is zonal direction of just an arbitrary example case, but what you'll note here is that the wave, after it's generated, is going to be refracted to higher frequencies as it passes through an opposing wind, to lower frequencies as it passes through a wind in its direction, and it's going to then emerge through a layer where it's actually nearly forced to evanescence, but then it, again, propagates into the thermosphere. So these fluctuations of the wind field provided by tides, all the ambient dynamics of the atmosphere, are going to be determining the fate of the gravity wave and its effects. And you'll notice all sorts of interesting things happen within a wave field that is sort of not just superposed, but directly interacting with that environment. So we're going to see this plot, I want to reinforce here, is showing the actual horizontal velocity, and the fluctuations associated with the wave are absolutely on the same order of magnitude as a typical HWM wind field, and in several cases quite a bit stronger. But they persist only as the wave evolves, but that wave, again, is going to have an ultimate effect on the state of the atmosphere, including modifications of the flow fields and cascades to smaller scales and connections to larger scales. So here we're going to start seeing some Kelvin-Helmholtz instability forming because the wave was shifted there to lower frequencies. The relative shear associated with the wave motions is greater. It also has grown to a large enough amplitude that it's prone to this sort of nonlinear dissipation, and over time this is going to get worse and worse. You're going to see the wave effectively breaking down into turbulence, and you're going to see impacts on the flow of the atmosphere there, where it's going to be modifying the winds, and it's also going to be radiating new secondary waves. So you can see here the birth of secondary gravity waves, opposing the direction of the original wave, but you also have this field of acoustic gravity waves that has emerged as a result of this breakdown. You can go forward, backward. These are new as a result of that wave dissipating. This is something that is seen in data if you look at the timing of evolution of events. So we can take a look at this. I'm going to go back here. We're going to boldly inspect this with scalar quantities instead of the wind field, which is, in this case, just the horizontal motion. This does not reflect the vertical motion of the fluid. So if you wanted to view both at one time, maybe you'd want to take a look at vorticity, but then you're missing all the compressions. You look at divergence, you're missing the circulation. So what I would like to visualize on the next slide are two scalar quantities: pressure for the lower atmosphere and Mach number for the ITM. The wave fluctuations are large enough at high altitudes to be measurable in Mach number. So the atmosphere is compressible. When you're looking at acoustic gravity waves, you're going to see fluctuation fields that, again, have many tens of meters per second fluctuations or greater in some cases. I'm also going to include the plots of species densities and a proxy for air glow, which is the product of hydrogen and ozone. So if you look at the three colors here, again, the green to blue glow is representative of the oxygen layer peak. The orange is the sodium layer, that's just the density layer. And the purple is the product of hydrogen and ozone, which mimics the peak of the hydroxyl layer, which is something measured by, for example, NASA's AW mission. So we can see here the red-blue is the lower atmospheric gravity wave field. You can see there's another. We actually excited some lower frequency wave incidentally as the source was active. But you can see here the phase structure of the gravity wave field as it's emerging, and you're going to just start to see some additional phase structure of the wave penetrating into the thermosphere. So as this wave evolves, you can see fluctuations in the species layers, and these kind of density fluctuations, again, you see in measurements. If you're looking at air glow, you're looking at LIDAR, you're going to see density fluctuations, and you can make comparisons between those. That's something that is commonly done in ground-based science, for example. But as we get to higher altitudes, you're going to see here the wave, again, is propagating into the thermosphere, so you have a higher speed of sound. You have, again, different winds, so you're going to have a slightly different wave trajectory, and you're going to see different scales at high altitudes because this packet is dispersing. So you're going to tend to see some of the lower frequency waves that are propagating more slowly at the lower altitudes, and you're going to see some of the higher frequency waves reaching higher altitudes. And as this continues to evolve, it looks different in the monitor than it does on the screen. I just want to apologize. The monitor has way better color, so I'm happy to share separately. Let me look this way here. Okay, now you can see the waves of the thermosphere. I've been staring at those waves in the thermosphere for a little while here, and I apologize. So you look at the structures as the wave starts to break down. You can see these sort of Kelvin-Helmholtz billow rolls, and this wave really is going to break aggressively. Now, let me note that this is a 2D simulation. I ran this on my normal desktop computer. It's maybe 125 meter resolution and in a single slice, but I will show in some of the talks later in this week three-dimensional equivalents of this. So you can imagine that if it's isolated, you're going to have additional effects and three-dimensionality emerging as you might be affecting only one part of the atmosphere at a time, and many sources are concentric, so they radiate evenly, but then after a while, half the waves might get filtered, so you only see it in one direction, and there's a whole bunch of neat evolutions that can occur when you look at gravity waves. So you see here the waves are still, the primary waves are still emerging in the gold here. So these, you can't see it, There's the acoustic wave spectrum up there. But you can see the primary waves are about to overturn, and these waves absolutely are the kind of thing you could see in an MSTAD. The little rolling motion here in the lower thermosphere is quite interesting and likely to happen. Meanwhile, if you could see them, there's secondary acoustic waves up there, and you're going to see the emergence of gravity waves as this wave field continues to break. Maybe some of these are actually visible. So, oh, and now these are breaking too. You see that here. So these dynamics below and above are things you wouldn't normally see if you're just looking at a fixed layer, and making those connections across one altitude region to a next is something that I certainly find compelling as a scientist, and visually appealing, actually, from the perspective of just looking at model results here. These secondary waves could absolutely drive an MSTID too, and those Kelvin-Helmholtz instabilities are going to lead to dissipation, but some of those waves are going to keep going. Now, while those primary gravity waves are not looking too good, you can see that there is the possibility of a second radiation region there as those waves have dissipated. In the region where it says force/acceleration, it turns out that those waves are also impacting the atmosphere, and you could see in the other figure an extension of red on one side and blue on the other as the literal pressure force is emerging from this wave's nonlinear evolution. You see standing wave structures now. Do you see that the waves at lower altitudes are actually sort of forming these standing wave patterns? After a while, this would establish a bunch of ducted waves. It would just kind of keep traveling through the stratosphere and mesosphere. And if this were a 3D simulation, that turbulence would just keep cascading down until some kind of final impact. So I wanted to share these as just a visual representation of wave evolutions and get you thinking about what is happening outside of a single layer. And I also am pleased to report that the ionosphere is, of course, heavily affected by waves arriving from below, as you can see in a lot of data sets. And this does contribute to that variability that you see over short time scales. For example, many minutes to hours. So happy to chat more, but I'll finish here now. Thank you very much.
That was great. Thank you so much. I just want to remind students, put your questions in the Slido. Any question you got, throw it in there. All right, our next talk will be by Dr. Fabiano Rodriguez. He's an associate professor of physics and electrical engineering at UT Dallas. He received his PhD from Cornell in 2008 and has been attending CEDAR since 2004. He's also affiliated with UT Dallas's Center for Space Physics, where he and his students contribute with experimental studies of Earth's ionosphere using ground-based instrumentation.
Can you guys hear me? Okay. So when Sophie asked me to give this talk, I had to task myself with what I wanted to talk about today. So here we go. How do we forward with this? I thought Jonathan had taught us how to use this. None of it is working. I see. Where did you point again? Oh, I see. You see? Maybe the battery is dying on this one. Let's try to do this. So these are the topics that I wanted to cover today. So I tasked myself to talk about equatorial spread F. You're going to hear this term several times throughout CEDAR. You also start hearing about it, some of the things related to equatorial spread F in the talks prior to this. I also wanted to talk to you about what causes spread F, so you go to these meetings throughout the week and you know where these things come from. And then I also wanted to talk about the relevance of equatorial spread F beyond fundamental science. We're going to have a lot of fundamental science throughout this week, but we also wanted to talk a bit outside that scope. And finally, I wanted to show you some fundamental studies with observations that my students have been working on, some new observations just to illustrate equatorial spread F so you can have a better picture of what it is. I like the way Jonathan gave a talk where he says, hey, I'm going to give you a graphical picture of what's going on. You're going to see equations, and you're going to hear these terms, but it's nice to visualize what's going on. So to be able to tell you what equatorial spread F is, I need to go back to vertical radio soundings. And nowadays, these instruments are called ionosondes, and they basically are ground-based radars. And the only difference is that they change the frequency, so they transmit a signal F, as illustrated here in this graph. And basically, the signal propagates up, and it is reflected at a region where the plasma frequency matches that signal frequency, and then it returns. From the travel time, you infer the distance at which that reflection occurred, and you also have this plasma frequency measurements as a function of height. And that's what we call an ionogram. And you can see on the right-hand side panel here on the top what an ionogram, a prototypical ionogram looks like. And if you look between 200 and 400 kilometers, you can see traces, and those are the regions where the reflections occur. And it looks like pretty neat observation. It's a clear ionogram, and you've seen this many times. But almost 100 years ago, people went to magnetic equatorial latitudes, and they see things that are more like the ionogram on the bottom right here. Instead of having a clear ionogram like you see in there, it's a spread in range, and it's spread at heights that are around at F region heights, and that's where the name comes from, equatorial spread F, okay? And the other thing that is interesting about those early observations, they figured out a few things almost 100 years ago. The first thing that they figured out is this comes from imperfections or irregularities in the ionospheric electron density. And they also noticed that that appeared when the ionosphere was uplifted a little bit around sunset hours, okay? Nowadays, this name, equatorial spread F, does not only refer to this spread in the ionograms, it has a more general name. And the name refers to the manifestation of interchange plasma instabilities that we see developing or having favorable conditions to develop at the magnetic equator. And the name of these interchange instabilities, they're referred collectively as the generalized Rayleigh-Taylor instability, depending on how the currents that drive them occur. And the situation that you have at the magnetic equator is the one that I illustrated right here. So you can see this is the configuration that I tried to illustrate what happens in the equator. So it's the electron density in color there as a function of height and a function of zonal distance. And you can see a current flowing to the eastward direction in X, and you can see this large gradient in the bottom side F region due to recombination during sunset hours when the bottom side is eaten away, and then you can see also gravity downward and the magnetic field into the page. And if you go and you take the plasma equations that Matt is going to cover in the next few slides, you can do a local linear instability analysis on those equations, and you can see that if you have a small perturbation in the bottom side, that perturbation can find favorable conditions to grow. And you can write a growth rate equation, linear growth rate equation, that is going to look like this equation right here. If you take into consideration currents driven by gravity and electric fields, the growth rate is going to look like that. And it has a multiplying term that is the gradient in the bottom side F region. It has this E over B that is the E cross B plasma drifts of the F region, and it has mu IN, which is the ion collision frequency. So it depends on how steep the gradient is, how strong the vertical drifts are, and the height at which these perturbations are found and the ion neutral collision occurs, okay? And then you can do more than this. You know, I've seen this equation when I was a grad student, and then I said, hey, I wanted to evaluate, and I kind of, how does it work? So you can go and you can take Joe Huba's model, for instance, SEMI2. Some of you are going to hear about this model that is open, you can download, and the model is an ionospheric model of the low-latitude ionosphere. And one of the things that the model asks you to do is to tell the model what the vertical drifts at the magnetic equator is, and it's going to output what the ionosphere and the thermosphere parameters are. And if you do that, if you take a prototypical vertical drift like the one that you see in here, this is a typical vertical variation, typical diurnal variation of the drifts that you see at the magnetic equator, and you drive the SEMI2 with those drifts, what you're going to get for the growth rate is something like this. What you're seeing now, we're just standing now, the colors represent the growth rates as a function of local time and height. And you can tell where the growth rates are large, and that's around the post-sunset region. And that simple local analysis of the stability of the equatorial ionosphere can explain a lot of things. For instance, you can explain why we see those irregularities associated with equatorial spread F right after sunset. You can also see that that explains some associations that we do with this so-called pre-reversal enhancement of the vertical drifts. If you look at the drifts around that curve around 18 local time, you can see there is an enhancement and then a reversal. That's something that occurs all the time at the magnetic equator. And the larger that value is, that peak is, the more likely is that you're going to see spread F. We still have to figure out a few other factors that contribute to the variability of spread F, but that's one of the main factors that control the development of that instability. Okay? So I will never be as proficient with modeling as these other folks are, so I just go and I grab model results from other people so they can illustrate things that I see with measurements. So this, what you're going to see here, is a visual representation, a model representation of what this instability is as it develops non-linearly, full development of a structure given that instability. And it's going to run now. And you can see that initial perturbation at the bottom, and you can see the interchange plasma instability taking place where the low-density plasma emerges and it goes into the top side. The scales that you see here are from the bottom side F region up to the top side, and you can see fluctuations that are with the scales of tens to hundreds of kilometers. And these large-scale fluctuations, they left behind also smaller-scale structures that are created by secondary stabilities. But the point that I wanted to make here is you have these large-scale structures, you have the secondary stabilities, these smaller-scale structures. So when you go on observations, you see structures varying from a few centimeters to several hundreds of kilometers. If you have a satellite flying through that structure, it's going to see a bite out in density, a decrease in density of several orders of magnitude. When you see that from a perspective of a satellite, you don't call that a spread F, you call that an equatorial plasma bubble. Okay, so you see this name throughout this week, equatorial plasma bubbles. Those are just the manifestations of just irregularities of equatorial spread F. They're observed by satellites or some other types of instruments, air glow imagers and things like that. Okay, moving on. The other thing that I wanted to talk about is this. So there's a lot of science related to equatorial spread F that you can spend time with. But there's also motivation behind it that it's the implication of spread F beyond fundamental science. The way I wanted to explain this is my ionosphere illustrated right there with the spread F developed. If you have a radio signal that is propagating through that ionospheric channel, it's going to go through drastic variations in the index of refraction. That index of refraction variations are going to cause signal fadings on the signal received by a receiver on the ground as a result of diffraction and refraction. And the equatorial spread F is recognized as being the event that causes the strongest scintillation fadings or ionospheric scintillation on signals in the globe. So one of the reasons people look at this is, now it's me changing hats from physics to engineering. Some people are interested in seeing how is equatorial spread F event affecting the signal, how is the phase or amplitude being changed, and also ionospheric delays being changed. And there are people in our field that study, the applications of this. Here, what I wanted to tell you is those variations in the signal, they affect different systems that we use nowadays for navigation, communication, and remote sensing. And all I'm showing here on the top panel in there is an example of a scintillation that we see observed at magnetic equatorial latitudes associated with equatorial spread F. The peak-to-peak variations in signal power is just maybe 10 to 15 dB, but they can be as large as 30 dB. In the bottom here, you see the ionospheric delay caused by those fluctuations by spread F, and you can see how drastic those changes are in the ionospheric delay. The other thing that I wanted to tell you is you're going to see during the week people talking about the S4 index. That's how much irregularities are affecting your signal, and the S4 index is nothing more than the standard deviation of the signal normalized by the mean value of the signal. So that number is going to come to play in observations that I'm going to show you later on. Now we covered what equatorial spread F means, where it comes from, the impact outside fundamental science. I wanted to talk to you about observations. And to talk about observations, I also wanted to mention the Jicamarca Radio Observatory is one of the NSF sponsored facilities at the magnetic equator, is one of the main sources of observations of the ionosphere at the low latitudes. And it's equipped with a large radar system that measures weak scatter from ion acoustic waves, but also measures scatter, Bragg scatter from those irregularities associated with equatorial spread F. And because it uses this large array, 300 meters by 300 meters, the beam is really narrow, so it points very localized over the region above Jicamarca. And the observations that you're going to see throughout the week are things like this. What I'm showing here is the RTI map. It's range time intensity. That's another jargon that we have in our field. It's basically telling you the signal intensity as a function of time and height. And you can see in red the echo returns coming from spread F. And you can see the plumes. Now I call them plumes. Those are equatorial plasma bubbles. Those are spread F going up to the top side. And this is a very specific type of measurement, very narrow. So what we wanted to do is we have spent time trying to figure it out how to make images of spread F with new systems. So we have repaired a system at Jicamarca that not only looks up, but it can also look sideways. It has electronic beam steering, so you can scan the ionosphere. And what you're going to see here are a couple of things. The first thing that I wanted to point out, there is an RTI map in there, hopefully right here, that tells you it goes from evening to early in the morning. So now what I wanted to point out is spread F is not occurring in the post-sunset, it's occurring almost sunrise. So that's an interesting event because it doesn't follow what we expected. But now what we're going to see is the question we have, is this something that was originated locally or something that originated much earlier on the other local time, longitude sector and moving into the field of view? And this type of measurements that we have now can tell you whether these events are local or non-local. And you can see now the development of spread F or these plumes or equatorial plasma bubbles occurring over Jicamarca, and they're local. Not only one, but two, spaced by about 200 kilometers apart. How many minutes do I have, Andrew? Two, okay, perfect. So the next thing that I wanted to talk about is this. One of the thrusts of CEDAR is to develop new equipment that is going to give us a better view of the system, of the Geospace system. At UT Dallas, I have some grad students that decided, hey, we need some more sensors in the lab, and we didn't have it. I didn't have the money, and they said, hey, we're going to come up with, we're going to go to Amazon, buy parts, and we're going to build ourselves. So they went ahead and they built this scintillation and TC monitors. There's a picture of one of them. What they do is they are GNSS or GPS receivers that you can buy for $40 now on Amazon, and you can buy a Raspberry Pi, connect to them, collect data, and they basically collect the signal that is the power that comes from the signals transmitted from GPS, GLONASS, or other GNSS satellites. So now for ranging from $100 to maybe $600, you can buy, you can build your own scintillation receiver. And they have been doing this. And not only they've been building in our lab, things like that, they've been deploying those. I'm going to skip this because I don't have a lot of time. But one of the science questions that we have is, when spread F develops, how high does it go? And why does it vary from day to day? Why some days we don't have it? And why does it vary with longitude? One of the the variability is important, and we wanted to be able to investigate how much that variability is, but we need to have distributed observations. So my students have been building these scintillation receivers, and they have distributing them over South America. This is Jose Maria, who has been doing this on his own. So he has his own network of GPS receivers over South America, and we're going to look at what it looks like. The dots here are the places where the signals pass through the ionosphere, and the color tells you how intense the scintillation is. So we're going to see now a movie throughout one night of spread F over South America. And you can see red happening to the eastern because the terminator passes there first. And then you can see scintillation is going up to maybe 20 degrees magnetic latitude. And you can also see both regions. You can study conjugate regions with those sensors. The other thing that I wanted to point out is you can see the dynamics too. If you look at Honduras, the stations to the bottom top left, you're going to see the structure. You're going to see red appearing first to the west, up, and then moves to the east. That is also telltale on how the structures are moving zonally, okay? I think I will stop here. I'm going to leave a couple messages. The first message is if you wanted to study spread F, or if you wanted to study things related to the equatorial ionosphere, you can spend 10 weeks at a Ricamarca. They will pay your trip, they will pay your stipend, you can go there and spend 10 amazing weeks just doing a lot of different things. And you can go also to Amazon, and if you have $100, or you can ask your advisor for $100, and you can buy parts on Amazon and build your own scintillation receiver. I'll stop here. All right, thank you so much.
Thank you very much, Dr. Rodriguez. That was a lovely presentation. Our next speaker is going to be talking about plasma physics, everybody's favorite topic. And that's going to be Dr. Matt Zettergren, who is a professor at Embry-Riddle, and his experience is in ionospheric modeling development and application to auroras and plasma structures.
All right. Let's see if I can actually make this work. Okay, so that does it. All right. It's like the rite of passage for the speakers. You have to play around with the thing and figure out how to get it to work. All right, so I was given the topic of plasma physics, or I wanted the topic of plasma physics because it's one of the things I'm most interested in. And then I immediately realized I probably need to de-scope that a little bit because, for example, at our university, there are no fewer than 3 courses, full semester courses in plasma physics. So I decided I'd put an ionospheric plasma physics modifier on that. And then further, I realized that there's a lot of aspects to that I probably couldn't cover, and I probably am not, in fact, even qualified to cover. So I kind of modified that further to look at spatial inhomogeneity. So I'm not going to be talking about kinetic instabilities, even though they're quite important in some regions. So I think there are no fewer than, as I counted, about 5 different sessions in the meeting this week that are dedicated to some aspect of plasma instabilities or related to some aspect of plasma instability. So I think it's a topic that you'll probably hear a lot about. So I've given some examples here of things that are sort of near and dear to my heart, and one of them is polar cap patches. So you have dense day-side plasma that can be moved into the cusp region where there are a lot of structured flows, and one model of this is these flow shears can kind of break these off into polar cap patches. This is a very simple representation. If you look at the actual formation of these in global models, they're quite a bit less straightforward, I should say, than this. But these plasma patches here have configurations, gradients that are in fact unstable, and I'll talk about the mechanism in a few minutes. And then as Fabiano just talked about, equatorial spread F, or the generalized Rayleigh-Taylor instability, is another source that's been an area of study for a very, very long time in our field. And I always like showing this plot from Keith Groves from the Altair radar and east-west scan, where you can see some of these beautiful structures in the plasma bubbles. And then, of course, you have Joe Huba's code that he's been using for many years to simulate these. And I'll talk a little bit about the study of these different plasma instabilities. So I probably don't need to cover this because I believe Kamal did a really good job of talking about the sort of composition of the atmosphere and ionospheric plasma, what produces it, where you're likely to see peaks in plasma densities. What I'm more going to focus on is sort of the paradigm in which we operate in ionospheric plasma physics, and that's what we call a weakly ionized plasma. And if you just look at the ionospheric F region, way down here, the density of the plasma is some 3 orders of magnitude less than the neutral atmosphere. So a lot of times when we're dealing with this area, we're very, very much focused on what the neutrals are doing to the plasma, or what happens to the plasma particles when they collide with the neutrals. And so I'm going to kind of start with that as a place to talk about the basic plasma physics. So your first E&M class, you probably talk about cyclotron motion, cyclotron frequency, Larmor radius, gyro radius, and this is just an example with an electron gun being fired into a tank with a magnetic field, and it forms a circle, and everyone's kind of used to talking about gyro motion. If you start adding more complications, for example, if you put a crossed electric field on this, what happens is you have a shortening and lengthening of the Larmor radius during different parts of the particle orbit, and you get what we call E cross B drift. So you've got this cycloidal, or whatever you call it, motion, but on average it's translating in the E cross B direction with velocity E cross B over B squared. So that's the next level of complication, and the final thing that kind of takes you from that to being able to do something pretty useful for ionospheric physics in terms of just physical descriptions is kind of illustrated here. So we have, this diagram's a little bit complicated, but I've got a dense atmosphere, and as you go up in altitude it becomes more tenuous. So at the very high altitudes where there's not a whole lot of atmosphere at all, really the drift is E cross B over B squared. As you go down in altitude, the collision frequency becomes high enough, it's of the order of the cyclotron frequency, so the particles can't complete a full orbit as they're trying to E cross B drift. And so what happens is they start to do an E cross B motion, this cycloidal motion, but they get stopped by these collisions partway through, and they have to sort of restart and so on and so forth. And so you actually pick up a drift both in the E cross B direction and then also in the direction of the electric field. And that just sort of leads us to one of our basic descriptions of plasma behavior in the ionosphere. And it's kind of shown here. Probably you've seen this picture. It's one of my favorites, but it's actually sort of complicated to work through. But it's showing sort of 3 components of the current density in the ionosphere: the parallel current, the Hall current, and the Pedersen current. In short, the Pedersen current is the current in the direction of the electric field. The Hall current is in the minus E cross B direction, and then the parallel current is, of course, along the geomagnetic field. Birkeland current is also how that's caused. So I just want to point out that the character of the currents kind of changes very severely with altitude. So if you start at 300, I'm going to start high and go low. The electron and ion drifts are almost the same. So a little piece of added information here is the electron cyclotron frequency is really high compared to the ions, and so the electrons will stay magnetized even when the ions are undergoing aggressive collisions. So the electrons E cross B drift, the ions are moving slightly different to that, and you end up with a bit of a net current, and it's usually quite small, and oftentimes we totally ignore the current at 300 kilometers in, for example, auroral situations, but in fact for some of these instabilities we talk about, that happens to be quite important. And then you get the standard picture as you go down in altitude where you have the ions demagnetizing further as they get interrupted during their orbits, and you end up with Pedersen and Hall currents at lower altitude. So I won't dwell too much on that. The basic idea is that we do have currents in the F region, and it's responsible, as Fabiano was talking about, for developing some of these instabilities. So I just want to mention, I'm not going to go through any of the linear theory. It's something you sit down and do pen and paper. But the equations describing a lot of the instabilities that you'll hear about are all actually kind of the same. You have some expression of conservation of mass, you have some expression of conservation of charge, and then you have some description of what the velocity of the particles are, or what the current is. And so I've listed that here. I guess the difference is sort of this first step is what is the current density? What particular forces are you taken into account in these different situations? And that's kind of what changes the different analyses that you'll see. And then the next step, if you're doing a sort of linear approach, is you linearize the equations. If you've taken a plasma physics course, you're definitely sick of doing this because that's like a quarter of the whole class is linearizing and doing waves. You have zero order background conditions, which this is where it's different from most like wave analyses where you just assume everything's constant with background. For these instabilities to work, you do need background inhomogeneities to sort of draw energy out of the background fields and so on and so forth. Then you Fourier decompose everything in space and time, and you end up with a dispersion relation with a complex frequency, which describes growth. So that's how the linear analysis goes. The algebra is substantial, but it's not difficult per se. What I'm going to do, though, is do some cartoon physics here. I was thinking about giving this talk, and I decided maybe the most helpful thing I could do is draw a bunch of pictures and Keynote and try to explain what's going on here. So I'll start with what to me it's the first instability I studied, and probably one of the easier ones to understand. None of them are that hard to sort of understand, but this is a so-called gradient drift instability, and this is something that operates in polar cap patches, we think, for example. And I apologize, I think the magnetic field direction is switching into and out of the page depending on which instability I'm talking about. I should fix that. But anyway, you have a E cross B drift in the direction of a plasma density gradient, and it's actually unstable. And so what I'm showing here is you have a corrugation, for example, on the trailing edge of a patch. And remember what I was talking about earlier, there is a Pedersen current in the direction of the electric field. And so if you just plot out what direction that is, what you'll realize is there's more plasma inside the patch, so you actually get a stronger current there than outside the patch. And what that leads to is you have this situation where you have strong current, weak current, strong current, weak current, and so on and so forth, which implies an accumulation in charge. And that's really the key dynamic that destabilizes the gradient drift instability. So every charge produces an electric field. And so if you plot those electric fields and you plot the corresponding E cross B drift from those first order perturbation electric fields, what you'll end up getting is electric field points from positive to negative charge, and then you do E cross B over B squared, and you get the velocity. You'll see these low density extrusions want to go farther into the patch, and then the high density patch regions want to go farther into the low density region. So this is a positive feedback that produces the instability. So anyway, I've written down the growth rates. I won't say too much about that. That's just directly from the linear analysis. So I'll talk about this generalized Rayleigh-Taylor instability a little bit, and I'm actually using one of Jonathan's wonderful pictures here. In the background is a seed perturbation, which is kind of another aspect of these instabilities. But this is the Rayleigh-Taylor instability, and Fabiano drew a good picture of this. This one's driven by gravity. Aside from E cross B drift, there's the general F cross B drift, which is charge dependent. And so other forces like gravity will generate a current. And you can have alternating high and low current densities because you have alternating high and low plasma density regions. So for example, on the bottom side, F region ionosphere, if you corrugate things or provide a seed perturbation, you can generate charge densities in E cross B drifts, which are sort of almost a sideways version of the last instability I showed you in terms of like where the charge is accumulating. And so in this case, as we talked about, gravity was the destabilizing influence, and I'm not suggesting that gravity waves are always the seed perturbation, but perhaps they could serve here. So that's Rayleigh-Taylor instability. And then the last one I'll talk about really quickly that you'll hear about oftentimes in the cusp ionospheric context is Kelvin-Helmholtz instability. And thankfully, I kind of have an easy job here because a lot of the stuff I'm talking about has been mentioned before. And so like you're sort of primed to think about these things. So Jonathan was showing some of the Kelvin-Helmholtz billows that form in the neutral atmosphere. And it's thought that similar things also happen in the plasma as well. In this case, Kelvin-Helmholtz is an inertial instability, so you need an inertial aspect in order to destabilize it. And you can think about it in terms of the ion drift theory that we had talked about kind of on a previous slide, where if you have a slowly varying electric field that's providing your E cross B drift, the particle orbits deviate slightly from E cross B over B squared, and it gives you an additional current that can actually destabilize the plasma. And these are just simulations that have been done by the University of Tromsø group that I work with. They tend to break because of the Ion-Pedersen current is what some of the initial work showed. I'm not going to go through this. I tried to plot out. This one's hard to visualize compared to the other instabilities, but you can show if you plot the polarization, the inertial current, you can show that there's a tendency to accumulate charge across a boundary layer. So I'll skip that in the interest of time, because I want to talk a little bit about nonlinear behavior, and Fabiano mentioned this, fortunately, so that speeds things up a little bit. One thing you'll hear a lot about is the quote-unquote spectrum of turbulence. Forming spatial spectra, for example, is one way that we study nonlinear behavior of unstable situations. And so the word turbulence is typically meant to use that you have some steady state energy exchange between modes such that there's a well-defined spectrum. And I'm showing, the most famous example here, which is the Kolmogorov spectrum, where you have some outer scale that's providing energy, you have some inertial subrange where you have unstable exchange between modes, and then you have some dissipation scale, which in an ordinary fluid would be like the viscous effects, which tend to dissipate energy. So this type of analysis can be done, and it describes the nonlinear state. It does not, however, describe the transition between linear and nonlinear, and it doesn't necessarily describe what's going on when you have variable forcing in your system. Things can get far, far more complicated. And so I just wanted to mention here, just to sort of plug my own area of research, a lot of times when we're studying nonlinear behavior, we're using computer codes to do that. They're a very good tool for it. The other thing that you can kind of do, and this is sort of just a cute thing that we do all of the time in physics, where you're looking at how important are certain physical processes. And the best example I could think of from sort of a regular physics class is when you're studying wave propagation through lossy media. A lot of times the pertinent parameter that tells you almost everything that you need to know is the ratio of conduction to displacement current. And in fact, I have it to the -1. I was going to say I have the numerator and denominator messed up here, but I actually don't. So I don't even remember my own slides. Okay, so anyway, you can do this for the instabilities as well, and you can ask yourself, what are the ratio of polarization to conduction currents? I'm sorry, folks. What are the ratios of pressure to conduction currents? And you can come up with different scale lengths that are important for different bits of physics in your plasmas. So I'm almost at the end here, so I'll just mention really quickly, an area of my research is doing these simulations using numerical ionospheric codes. And Fabiano showed the results from Tatsuya Yokoyama's code for equatorial plasma bubbles, and we do something pretty similar with our Gemini ionospheric model too. We study all of these instabilities, although I have done far less with Rayleigh-Taylor than anything else. But I do have some examples if you have interest in running codes and looking at this. I won't say they're easy to use, but they are actually online here, and I'm happy to talk to you about them and help you set them up. I will warn you that the examples I have aren't quite as good as what's listed here, because I ran these on a really large workstation, and if you're running them on your laptop, the resolution is going to be worse. Okay, I'm definitely out of time. So Fabiano thankfully covered the radio impacts of these types of structures. I'll just say they're significant, and you'll hear about them over and over again. Scintillation is one aspect, but you also have other things going on affecting, for example, the accuracy of geolocation and so on and so forth. So I'll stop there because I went over a little bit. Sorry.
Oh, that was great. Thank you so much. And now we're going to move on to our final lightning talk of the day, given by Dr. Roger Varney. Dr. Varney is a professor in the Atmospheric and Oceanic Sciences Department at UCLA, specializing in upper atmospheric physics and magnetosphere-ionosphere coupling. His research combines numerical modeling of the coupled magnetosphere-ionosphere-atmosphere system with observational data analysis, especially of ionospheric data from incoherent scatter radars.
Okay, thank you very much. So I have been given the impossible task of explaining how the northern lights work in only 15 minutes. But this is an important thing to know how to do because this is one of the most common questions you're going to get from the general public as a space physicist. What actually causes the northern lights? Especially now that we had that giant storm on May 10th, where lots of people got their first opportunity in their life to actually see the aurora. So let's see if I can do this. Yes, spotlights and moving forward. So if you just Google what causes the aurora, the short explanation is energetic particles hitting the upper atmosphere and exciting molecules. So if you, this is an infographic from NASA for the general public that we use all the time in our education and outreach activities. The basic idea is you have energetic particles, mostly electrons, that are coming down from the space environment, hitting molecules of the atmosphere, exciting them into excited states, and when those molecules relax down, they emit photons as very specific wavelengths in very specific colors. This is a good first cut, although it glosses over a lot of details. Perhaps one of the most misunderstood facts of the aurora is that most of these energetic particles are not coming directly from the sun. They're actually coming from different parts of the magnetosphere, and so most of the complicated dynamics that you're seeing are actually reflecting how ungodly complicated magnetosphere-ionosphere coupling actually is. And when you try to explain the aurora in more detail than this, you quickly run into the problem that aurora is not one phenomena, but actually a whole class of different phenomena. There are multiple different types of auroras, and the physics behind them is different. And our field doesn't really have a uniform way of categorizing auroras. So one of the things that I thought about very critically when putting together this talk was, how do we even classify auroras? How would we go about creating a taxonomy of aurora? One thing you can look at is particle energies, which are directly related to how deep they go in the atmosphere and what colors get produced. The other way is to talk about acceleration mechanisms. So how are the particles actually getting energy? Are they coming directly in from the solar wind and magnetosphere in the cusp? Or are they trapped particles from the inner magnetosphere that are being pitch angle scattered, which was the diffuse aurora and pulsating aurora fit in that category? Or are they being accelerated by electric fields parallel to the background magnetic field, like discrete aurora and alphanic aurora? And then the last way to go about categorizing auroras would be on their location, morphology, and dynamics. And there's a whole bunch of terms in the literature like quiet arcs, streamers, polar boundary intensifications, omega bands, torches, patchy pulsating aurora, flaming aurora, flickering aurora. I could go on, and all of these terms are actually technical terms with defined meanings. So the first thing to understand is the higher energy a particle is, the deeper it will go in the atmosphere, right? So I'm showing results from an ionospheric transport code and also the parameterization fit to them from Fang et al. 2008, which is a pretty to use empirical parameterization alternative to running a full up electron transport code. The particles of energies of a few hundred eV will land in the F region ionosphere. So 100 eV or so will land around 200 kilometers altitude. It'll heat the F region ionosphere, and that is mostly going to produce the 630 nanometer red line. The 1 to 10 keV-ish particles are actually going down to the E region. So 1 keV goes to like 120 kilometers, and they produce a lot of the green line. The higher energy particles go progressively deeper. As you go deeper and deeper, you get more and more of the nitrogen emissions. And the really high energy stuff, the 100 keV to 1 MeV, is going all the way deep into the mesosphere to 60 kilometers or so. And those very high energy particles don't have much of a signature in optical emissions, but they're actually really important for atmospheric chemistry, because the particles that are going that deep into the mesosphere are producing lots of odd hydrogen and odd nitrogen, HOX and NOx, which then have catalytic ozone destruction effects and all these knock-on effects to mesospheric chemistry. So I mentioned the green line and the red line a bunch. If you just look at the band diagram of atomic oxygen, The three lowest lying states are the triplet P state is the ground state, the singlet D state is the next one up, and the singlet S state is the next one above that. The transitions between these states are optically forbidden. They cannot proceed through the electric dipole transition. So these are actually metastable states, and these forbidden transitions have finite lifetimes. So whether or not they manage to make these transitions or not depends on whether or not the molecule collides with something else before actually relaxing. So the red line transition is the singlet D to the triplet P transition. And that singlet D state actually has a fairly long lifetime. It's over 100 seconds long. The green line is the singlet S to singlet D transition. And that is also a forbidden transition, but it has a considerably shorter lifetime. And that ends up explaining the colors from different altitudes. So it's quite common to see auroras that look like this, where you have green on the bottom and an extension of red on top. Basically, the atmosphere gets thinner and thinner the higher you go. So if you're going to emit a red line photon, then a singlet D, an O singlet D has to emit that red line before it collides with some other neutral and relaxes. If it collides with another neutral and gives up its energy to that other neutral without emitting a photon, in the optics literature we refer to that as quenching, because the energy has gone away without creating any light. So at low altitudes, the mean time between collisions is considerably higher, and so you will optically quench the red line emission, although you won't quench the green line emission, because the green line emission is 2 orders of magnitude shorter lifetime. As you go deeper and deeper into the atmosphere, nitrogen becomes more and more important. Nitrogen is a molecule, not an atom, and the quantum mechanics of molecules are so much more complicated than the quantum mechanics of atoms. But in a nutshell, there are 2 band groups that we care about when talking about visible emissions from nitrogen. The first is the so-called N2 first positive group, which are emissions from excited neutral N2. And there's a whole bunch of lines that are in the red and near infrared from that. And then there's the N2 plus first negative group of emissions, which are you have an electron that will collide with N2 to produce N2 plus in an excited state. And the excited state of N2 plus will relax to the ground state of N2 plus and emit photons. And probably the most well-known emission in this group is the 4278 so-called nitrogen blue line. And the red lines and the blue lines tend to mix together into something that kind of looks pink or purple. So when you look at an aurora like this, where the bottom edge of it is all pink, those are multiple nitrogen emissions mixing together to make that pinkish color. And these are probably electrons of 10 keV or so to be penetrating deep enough to actually get that pink lower edge on the bottom. So I want to move on to talking about particle access to the upper atmosphere. I mentioned that most of these particles are not coming directly from the sun, which is a common misunderstanding of how the aurora works. It's actually pretty hard to get a particle from the solar wind to the upper atmosphere because of the way the magnetic field works. Most of the particles are diverted around Earth's magnetic field, and the only particles that have direct access to the upper atmosphere are the ones that get funneled down this feature that we call the magnetic cusp. So there are some particles that get funneled through the cusp and produce the so-called cusp direct entry aurora. Those particles have energies of a few hundred eV at most. So they're only going to produce red line emissions, and they're only going to produce emissions on the day side immediately below that cusp. So almost all of the aurora that you see in pictures are actually magnetospheric particles that have been accelerated through all kinds of other mechanisms from the complicated plasma physics going on throughout the rest of the magnetosphere. A big part of why it's hard to get particles into the upper atmosphere is because of the so-called magnetic mirror force. So in a plasma physics class, you'll talk about this concept called the first adiabatic invariant, which is an approximately conserved quantity for particle motion in a non-uniform magnetic field. And the conservation of the first adiabatic invariant leads to this effective force, the so-called mirror force, which basically pushes particles away from regions of strong magnetic field. So in the inner magnetosphere, particles will be trapped in these trajectories that will bounce back and forth in the dipole field because the mirror force is pushing them. This is how you capture the Van Allen radiation belts. It's how you hold most of the magnetosphere out there. And the particles can't actually get down and touch the atmosphere. To get down and hit the atmosphere, they have to be moving so close to parallel to the background magnetic field that they're in the so-called atmospheric loss cone. It's a very narrow range of angles. For L of 4, it's like 5 degrees wide. That is so close to parallel to B that the magnetic mirror force doesn't apply and they can actually come down and hit the atmosphere. So there's an entire class of aurora that are particles from the inner magnetosphere that are scattered into the loss cone by some process that breaks the first adiabatic invariance. So the so-called diffuse aurora is emissions that don't have much structure to them and are kind of broad. And the diffuse aurora is particles from the inner magnetosphere undergoing wave-particle interactions and being scattered into the loss cone. There are entire sessions at the GEM meeting on these wave-particle interactions. It is an incredibly complicated topic. This is the summary figure from Richard Thorne of the various different wave populations in the inner magnetosphere. Different types of waves prefer different types of regions. There are waves that prefer to be inside the plasmasphere versus waves that prefer to be outside the plasmasphere. In particular, these waves that are called chorus waves that exists mostly on the dawn side and outside the plasmasphere are thought to be extremely important for creating the diffuse aurora. I'm showing here a spectrogram from CRESS, and the chorus waves are these bands of emissions between 1/10 and 1 of the electron cyclotron frequency. So Whistler mode chorus. The chorus waves are high enough in frequency that they are comparable to the particle's gyro frequency, and the adiabatic theorem breaks down, and they can actually result in pitch angle diffusion, violation of the first adiabatic invariant, and some random scattering of the particles all the way into the atmospheric loss cone. Wave-particle interactions are also super important for the pulsating aurora. The pulsating aurora is this really eerie phenomenon where you will see patches that will blink on and off with with periods of 2 to 20 seconds. And we know from comparisons of ground-based optical imagery and satellites that there's actually a temporal correlation between bursts of chorus waves and these individual blinking on and off of the pulsating aurora. So the diffuse and pulsating aurora are dramatically different from the so-called discrete aurora. The discrete aurora looks like these very well-defined curtains, these very well-defined structures. So it doesn't fill the whole sky. You actually see very well-defined curtains. These curtains are sheets of upward field line current. And you can figure this out just by flying rockets through them, right? So if you think about a sheet of upward field line current and you use Ampere's law on your right-hand rule, then as you fly through a discrete arc from south to north, you should see the magnetic field rotate from eastward to westward. And this is one of Christina Lynch's sounding rockets, and you see as the rocket traverses this particular discrete arc, you actually do see exactly this rotation on the onboard magnetometer. So Matt already introduced field line current systems. There is this large-scale current systems between the magnetosphere and the ionosphere, the so-called Birkeland current systems, and embedded within those, there are smaller scale field line currents that are related directly to the discrete auroral arcs. So when you look at this from DMSP, here are ultraviolet measurements from the SUSY instrument on DMSP, and also magnetic field measurements and particle measurements. The decreasing green line is the sign of magnetic field variation that corresponds to upward field line current. And so you are seeing DMSP go from the polar cap through the region 1 field line current and the region 2 field line current. And this region 1 upward field line current region on the dusk side is where you see these accelerated particles. In the satellite literature, discrete aurora is sometimes called inverted V aurora or monoenergetic aurora because of what it looks like in these spectrograms. You see a beam of essentially electrons all at the same energy, and this structure where it ramps up to an energy and ramps back down, the so-called inverted V. So how does the inverted V actually form? Well, parallel electric fields are involved, right? So I mentioned that the mirror force is keeping electrons out of the upper atmosphere. Well, if you need to carry an upward field line current carried by negative electrons moving down to the ionosphere. How do you do that if the mirror force is keeping them back out? Well, nature finds a way, and it finds a way by violating ideal MHD, and kinetic physics happens that actually forms double layers and parallel electric fields a few thousand kilometers above the ionosphere. So this is so-called auroral acceleration region, and here are direct examples from the FAST satellite of fast flying directly through one of these so-called auroral cavities. And when you're inside the cavity, you actually see beams of upward accelerated ions. Because if I have an upward pointed parallel electric field that is shooting electrons down into the upper atmosphere, it is also shooting ions up in the other direction. And this has all been, that these parallel electric fields exist has been confirmed by multiple satellite missions at this point. What I just described is the so-called quasi-static acceleration, where you have basically DC parallel electric fields. There are also acceleration mechanisms involving interactions with Alfvén waves. So in the same auroral acceleration region, if you have so-called inertial Alfvén waves, they have their own parallel electric fields that will also accelerate particles. So ideal MHD says that an Alfvén wave has no parallel electric field, but once you start adding in some of the non-ideal MHD effects, you get to the so-called dispersive Alfvén wave regime, the inertial Alfvén wave regime, and they really do have parallel electric field components. And they result in aurora that looks considerably different. So this is an example where you can see both monoenergetic and alphanic aurora in the same pass from FAST. So there is a region here of, this is your so-called monoenergetic aurora in a region of upward field line current based on the sign of delta B. But then there are these other features that are a broad spectrum of electrons across a wide range of energy. And that so-called broadband aurora is where you also see wild fluctuations in the electric field. So the broadband aurora is your so-called alphanic aurora. And instead of being at all at one energy, it's at a whole range of different energies, and so they'll go to a whole range of different altitudes. I do not have enough time to talk about all the different types of mesoscale forms that have been defined. If you're really interested in that topic, I really recommend this review paper from Space Science Reviews. But this is just one figure from that paper showing, these are polar images showing what's called a polar boundary intensification, where you see a sudden thing appear at the polar boundary, streamers, which are propagating structures from the polar boundary down towards the equatorward part, and the streamers are thought to be the ionospheric projection of what we call bursty bulk flows in the tail. And then you also notice that the equatorward part of the aurora has all these wiggles on it. Those wiggles are actually called omega bands because they kind of look like the Greek letter omega. And this is actually showing streamers coming down and interacting with those omega bands and forming different pieces of them. The last thing I'll mention is substorms. The term substorm is wildly confusing because substorms can happen either during storms or non-storm times, and I don't really like the terminology. A substorm is really an impulsive release of a lot of magnetic energy from the tail all at once. And if you look at a single substorm cycle, it looks something like this. You see the so-called growth phase arc, which is a stable arc during a time when the magnetotail is stretching and the current sheet is thinning. And then there will be an onset where that arc very suddenly brightens and a whole bunch of energy is being released from the magnetotail all at once. And then after onset, you will transition into the so-called expansion phase, where it will expand poleward, and you actually see this WTS in this diagram stands for westward traveling surge, because this giant head will actually move towards the west. So I'm gonna finish with a movie from the International Space Station during the September 2017 storm. And I really love this movie because you can see all the different types of aurora I just talked about all at once. The spacecraft is orbiting from the dust side towards the dawn side. You see these tall rays that are probably alphanic because they have a low energy, a red top. And then look at the pulsating aurora as we get into you can see all these pulsations turning on and off, and the bottom edge of the pulsations are pink because the pulsating aurora is so energetic that you're getting lots of nitrogen emissions in the process. And I'll stop there.
All right, that concludes our lightning talks, and I'll go ahead and I'll read some of the questions from the Slido now, and then we got microphones for all the speakers. Perfect, I'll just start from the most upvoted questions. So question number 1 for Dr. Jonathan. 1, does gravity waves influence the formation and propagation of traveling ionospheric disturbances?
So I guess there's two relevant answers to this, and it's a good question. There's definitely a class of traveling ionospheric disturbances that are probably just gravity waves directly driving the ionosphere. So some fluctuations you see, especially if you're looking at the maps of GNSS total electron content over the US, you'll see really clearly wave structures that are just the direct basic motions of gravity waves as they're colliding with the ionosphere. You also likely have some role of gravity waves in providing some seeding, as Matt Zettergren was talking about, where some other instabilities can arise that would have forms of ionospheric structuring or perception of ionospheric motion that would be associated with ionospheric dynamics triggered by the underlying seed fluctuations. So yeah, I would say definitely gravity waves do influence the formation and propagation of traveling ionospheric disturbances, because a lot of traveling ionospheric disturbances, especially at mid-latitudes, are due to gravity waves from below. Another part of that question, though, is that at high latitudes, you're going to have gravity waves driven by the basic auroral inputs to the atmosphere, and those are going to be of a very different scale and character. So large-scale traveling ionospheric disturbances are quite distinct from the sort of medium-scale ones that we're talking about at mid-latitudes from below. So,
Great.
If that helps a bit.
And I think while you've got the microphone, the second question is also directed towards you.
Yeah.
What are the correlations between gravity waves, secondary gravity waves, and the intensity/frequency of TID events?
Yeah, so the secondary gravity waves, it's a good point. A lot of waves that we see at mid-latitudes in for example, total electron content data sets are going to be associated with weather. And many of those are persistent and generated far after the evolution of the initial onset of the system. So if you look at the timing of specific convective events, you're going to see kind of two parts of it. You're going to see first the primary acoustic and gravity waves that will arise shortly after the early evolutions, and those clearly are timing well with, for example, rainfall, et cetera. But later on, you're going to see persistent radiation of often concentric gravity waves, and these are likely also secondary waves or waves that were trapped in the sort of atmosphere below mesopause that just continuously leak out. So you'll see kind of a sequence of wave populations in the thermosphere and ionosphere, and a good fraction of those are almost certainly secondary waves. So,
Great, thank you.
thanks.
And then our next question is for Roger. Is different types of aurora, e.g. diffuse and discrete, more related to different energy level particles or from different parts of the magnetosphere?
So the short answer is that they come from different parts of the magnetosphere and they're accelerated by different mechanisms. So both the diffuse and the discrete will commonly be a few keV and produce mostly the green line, but the magnetospheric plasma physics producing them are completely different. For diffuse aurora, you're talking about particles that were trapped in the inner magnetosphere in this pitch angle bounce motion and got somehow, probably through a wave-particle interaction, diverted such that they were almost parallel to B and they were able to come into the atmosphere. And that pitch angle diffusion does not involve a paraelectric field at all. It's just scrambling the pitch angle of the particle. Discrete aurora is actual acceleration through paraelectric fields in the so-called auroral acceleration region. So the discrete aurora absolutely requires the E parallel and the so-called field line potential drops in order to form it. And the discrete is what is directly associated with current systems, with upward field line current.
Great, thank you. I think we have time for one more question directed towards Dr. Rodriguez. If you could raise, oh, there you are in the back. What is the minimum data acquisition rate necessary to measure scintillation?
We've done tests with it. the minimum would be 10 hertz. We can't really differentiate because, and that's based on the typical fluctuations that you expect to see on the signal patterns that you observe on the ground that can be as low as 0.1 seconds. So we wanted really to have, looking at the Nyquist frequency, maybe 20 hertz, but you can still get a lot of information from 10 hertz.
Perfect, thank you so much. That's all the time we have for questions right now, but we'll go ahead and take a 10-minute break, and we'll come back at 11:10 for our next session. Thank you so much.